All right, so now let's do the third practice exam, answering the questions that are applicable to your third midterm exam. So the first question is a redox balancing problem, which in this exam was graded as all right or all wrong, so let's try to go through this carefully. So the first thing to do is go through and assign oxidation states of all the elements and all the molecules to figure out what was oxidized and what was reduced, so we can isolate our half reactions. So for chromium tetrahydroxide, we don't have a chromium rule, but we do have an oxygen rule and a hydrogen rule. So oxygen's -2, hydrogen is +1, for a net of -1, which means the total contribution when there are 4 of them is -4. Chromium, in order to make the entire species a -1 charge, has to be +3. There's only one chromium, so it is +3. Hydrogen peroxide, the hydrogen rule trumps the oxygen rule, so +1, +2, so therefore -2 to make it neutral. There are 2 oxygens, so that's -1. Dichromate, oxygen's -2, 4 of them for -8. Overall is a -2, so chromium has to be +6. There's 1 of them, +6. Water, +1, +2, -2, -2. All right, so we're going to isolate our half reactions. In order to do that, we have to identify what has been oxidized, what has been reduced. So chromium, we go from +3 to +6, so that is a 3-electron oxidation. It has lost electrons, so something must have been reduced. So hydrogen's the same all the way through. So the only other element is oxygen, -2 and -1. So we have 2 different oxidation states here. Not a big deal as long as we don't have 2 over here, and both oxygens on this side are -2. So oxygen, since we're already going from this chromium molecule to this chromium molecule, we'll have this be our second half reaction, where peroxide is going to water, which is a 1-electron reduction. So let's balance our half reaction separately. First is chromium H4-, and that is going to chromate CrO4-2-. So the first step is to balance the element being oxidized or reduced. There's 1 each, so we're all set. Then we balance the oxygens using water. We have 4 of them, we got 4 of them. That's all set. And then even though it says basic conditions, again, we went through 2 different ways to do this in lecture, but for me, the way that's easiest for me to get through is just to memorize the acidic way, and then to cancel out or to neutralize your protons with hydroxides, and then cancel superfluous waters. And so let's do it in acidic conditions and then turn it into basic conditions subsequently. And so with that rule, we have 4 hydrogens over here, none over here, and so we need to add 4H+. And then finally, we balance the charge using electrons. We have -1 in aggregate over here. We get -2 and +4, so that means in aggregate it's +2. In order to turn both sides the same, you can only add negative charge, so we need to add 3 electrons to make this whole side -1, right? So -3 + 4 is +1, -2 is -1, which works out over there. So that is all balanced, but we're just going to go ahead and convert this to basic conditions, and we do that if there's 4 protons, we add 4 hydroxides to each side. So on the left, 4OH-, and on the right, 4 protons plus 4 hydroxides equals 4 waters, and then we'd want to get rid of extra waters, but there aren't any on the reactant side. So that is done. And then we take the other half reaction, hydrogen peroxide going to water, balance the element which is being reduced to oxygen, 2 oxygens, 1 oxygen, so double that. Then we balance the oxygen, but that was the element being reduced, so we can skip that. Then we balance the hydrogen using protons, 4 hydrogens, 2 hydrogens, so we need 2 protons. And then the charge with electrons, nothing charged over here. We can add negativity over here, so we'll add 2 electrons to balance out the charge. And then again, we turn this into basic conditions by neutralizing the H+ with hydroxide, and so adding 2 hydroxides to the right side is that, and then adding 2 hydroxides to this takes 2 protons and turns it instead into 2 waters. And then we balance superfluous waters, and we've got 2 waters and 2 waters, so that simplifies down quite nicely. All right, so now we have completely balanced half reactions and basic conditions, and then before we add them up, we need to rearrange our stoichiometry such that electrons cancel. So we have 2 electrons and 3 electrons, so common denominator is 6, so we have to multiply this whole sucker by 2 and this one by 3, and then go through carefully and add everything up. So 2 chromium tetraoxides, 2 CrOH4 minus, and then we have 8 hydroxides. And then down the reactant side for the second one, 3 H2O2 plus 6 electrons, right? 2, 8, 3, canceled, 6. And then on this side, gotta carry that 2 over here, 2 chromates, 2 minus, 2 plus 6 electrons, plus 8 waters, and then down here we have 6, 2 times 3 hydroxides. All right, so before we transfer that answer into our answer box, let's simplify it. So if we've done this right, and we have 6 electrons that are being canceled, and then we have 8 hydroxides and 6 hydroxides, so we can get rid of all of those and turn this into 2 hydroxides, and then there are no waters over here, so everything else should be balanced. So make sure when you transfer this down to your answer that you reintroduce states of matter. So this is an aqueous, and then we have 2 hydroxide, aqueous, and then we have 3 hydrogen peroxide, aqueous, going to 2 chromates, aqueous, plus 8 waters, liquid. All right, so before we call this done, let's just double check. Going back to our half reactions, before we multiplied them out, we had said before that chromium was undergoing a 3 electron oxidation. 1 chromium plus 3 electrons, that works. We said oxygen was undergoing a 1 electron reduction, so we have added 2 electrons, but there are 2 oxygens, 1 for each, so that works out. And then we paid attention to all our atoms and all our charge, but let's just go through at the end and hope that we have it messed up. So charge, we have 2 minus plus another 2 minus, that's 4 minus, 2 minus, double it, 4 minus, that's good. Chromiums, 2 of them. Oxygens, that's 4, double that is 8. Another 2 is 10, another 6 is 16. 4, 2 is 8, plus another 8 is 16, we're good there. 4 hydrogens times 2 is 8, plus another 2 is 10, plus another 6 is 16, and then 2 times 8 is 16. So I am confident that we have that correct. Awesome. All right, so for the reaction in problem 1, identify the following, the reducing agent. So the reducing agent is what gets oxidized, thereby giving its electrons to something else to reduce it. So the species that was oxidized was not chromium, but the agent itself was chromium tetrahydroxide, CrOH4 minus aqueous. Okay. The oxidation state of chromium in that molecule, we actually already went on through that work, and that is +3. And then the oxidation state of oxygen and peroxide, again, we've already done that work too, as we needed to have solved this equation. That is -1. All right, problem number 3. The reaction 2 ammonia to yield 1 mole of nitrogen gas and 3 moles of hydrogen gas. Equilibrium constant of 7.6 times 10 to the -3 at 900 Kelvin. Predict the thermodynamic signs. All right, so the first one that we can do most easily is the standard state free energy change. So the standard state free energy change equals negative RT times the natural log of K. And so the only thing that matters is whether this is greater or less than 1. So because it is less than 1, that means that we'll have an ln of that number that is negative, which means the whole delta G will be positive. So in other words, that is an unfavorable reaction in the standard state. Now, enthalpy is a little bit harder to just divine. Looking at this reaction and all that information really helps us. So let's skip ahead to entropy. And so entropy, simply put, we have 2 moles of gas that are reacting to yield 4 moles of gas. And so by doubling the moles of gas, that is inherently a more entropically favorable situation. So the entropy is favored, and a positive entropy means that it is favored. So in other words, based on those two, let's figure out what's going on with the enthalpy change. And so it's a good idea, delta G equals delta H minus T delta S, right? So if we know that the total free energy change has to have a sign of plus, and this does have a sign of plus, which means this whole term will be negative. So clearly we have something where the delta G is going to be temperature dependent, but since we're dealing with one particular temperature, the only way in which the free energy change is positive, given that this whole thing is going to be negative, is that if delta H is also itself positive. So that's how we get to that. All right, the KSP value for calcium fluoride is 4 times 10 to the minus 11th. The balanced equation for the reaction to which this refers, including states, and calculate the molar solubility in pure water. All right, so KSP is simply the dissociation of a solid to give the aqueous ions. And so we have calcium, this we can just put right in here, and that's a solid. And you have to use an equilibrium arrow since we're talking about an equilibrium constant. And then we have calcium, which is a 2+ cation, aqueous. And then we have fluoride, which is a 1- anion, 2 of them, which are also aqueous. So now we need the molar solubility given that KSP value. So we can actually do an ice table right underneath this equation we just did. Now, ICE, this doesn't participate in the equilibrium constant expression, but we're still going to need to know that quantity. So to figure out the solubility, we have some amount of calcium fluoride solid that will take pure water that doesn't have any calcium or fluoride and yield X moles or X molar of each, or sorry, of calcium. And this, of course, is plus 2X, and then X, 2X. And now we can set up an equilibrium constant expression where our KSP value is X times 2X collectively squared, which is going to be 4X cubed. And we can set this equal to 4.0 times 10 to the minus 11 as the KSP value. Take that over here, we have more room. And so we're going to divide that, both sides, by 4. So x cubed is going to be 1 times 10 to the minus 11. And then we take the cubed root in our calculator. Okay, so let's just go through all that. 4 times 10 to the minus 11th. Oops. 4 exponent 11 minus, and then we divide that by 4. 1 times 10 to the minus 11th, and then we take the cubed root of that, which is the same thing as taking it to the exponent of 1/3. So we can do x to the y 0.33333333, and we get 2.15 times 10 to the minus 4. Okay, so that is the x value in the equilibrium constant expression. Now, in order for that concentration X to been yielded, we're defining that as the molar solubility. So even though this does not participate, what we do is imagine calcium fluoride as an aqueous and yet associated unit, then fully dissociating, and the stoichiometry being 1 to 1 with respect to that X value. That X value is indeed the molar solubility. And so to 2 sig figs, 2.2 times 10 to the minus 4 molar. All right, so with the molar solubility of this solid compound increase, decrease, or stay the same in the following solutions compared to water. All right, so now we're looking for common ions or solutions that have components that will react with any of the other species that we have in our solution. So sodium chloride is an ionic compound, fully dissociates, and so neither one of which is going to affect pH. So we have pH neutral sodium, pH neutral chloride. So now we just need to figure out if we have any common ions. We don't, and so the solubility will be essentially the same. Sodium fluoride, another ionic compound. Fluoride is not pH neutral, but we actually don't need to worry about that. All we know, again, sodium doesn't matter, is that fluoride is in fact a product of the reaction. So if we have an existing quantity of fluoride, less of it will go into solution because this will not be 0, and so it will drive the equilibrium further to the left, which means the molar solubility would decrease. Hydrochloric acid, so fully dissociates H plus and Cl minus. Chloride is not a common ion, it is pH neutral. Of course, H plus is certainly not pH neutral, it is an acid, and then we just have to ask if anything here is going to react with an acid. So calcium, its pH is going to be, if anything, acidic as a Lewis acid. Fluoride, going back to exam 2, is the conjugate base of a weak acid, which means it itself is a weak base, and so the protons will react with fluoride to make hydrofluoric acid as an associated weak acid, which means it'll drive the whole equilibrium to the right, thereby giving an effective increase in molar solubility. All right, calculate the standard state entropy change for the formation of liquid water from elements in their standard reference forms at 298 K. And so formation of liquid water from reference elements, and so liquid water is our product, and then with the reference forms of hydrogen, H2 gas, and the reference form of oxygen is O2 gas, and so then we just need to correct the stoichiometry by multiplying that by 1/2. So the standard state entropy change is going to be the entropy of liquid water minus the sum of the entropy of hydrogen gas plus 1/2 the entropy of oxygen gas. Now these are not values you have to memorize, and so on this actual exam in 2015 was a front page that had an equation sheet. So we'll just use the textbook to dig up these values. Have it bookmarked here. All right, so we need the entropy of liquid water. So I think that shows up. Where does that show up? Oxygen, liquid water, sorry. All right, so the standard entropy is the third column. Liquid water is 69.91. So 69.91. And then we need the standard molar entropy of hydrogen gas. So hydrogen is here. H2 gas, the standard entropy is 130.58. 130.58. And now the standard entropy of oxygen gas is plus 205.0. 205.0. And then we have to divide this by 2. And let's keep in mind here that the units of all of these are joules per mole Kelvin. All right, so now we just have to type all this into our calculator. My So close the book up. So we have 205, and we divide that by 2. And then we're going to add that to 130.58. And then we have to flip the sign of that, because that's what we're subtracting from 69. And then therefore add it to 69.91. So I get negative 163. And sig fig wise, we're cut off at the 10th place here, so we'll do that. Minus 163.2 joules per mole Kelvin. All right, the reaction described in number 5 is spontaneous at, and so we have to ask, we have to figure out what the sign of delta G, delta S, and delta T is, or at least of delta H and delta S. So let's just do that. Reaction, delta H minus T delta S. And so if we just look at the, we have 1.5 moles of gas becoming liquid, so that is absolutely not entropically favorable. So the delta S is going to be less than 0, unfavorable. As far as enthalpy is concerned, we are talking about a reaction which we know very well to be overall spontaneous and very, very exothermic, right? H2 is rocket fuel, and when that explodes, it releases a tremendous amount of heat. So that means that delta H is going to be negative also. And so the delta H is negative, the delta S is negative, which means this thing is positive, which means in order for the whole thing to remain negative, the T has to be relatively low, so lower temperatures. Okay, and one more question for exam 3, numbers 7, 8, and 9 we did for exam 2. Determine the oxidation state, most likely coordination number of the metal center in iridium, Br2, cyanide 2, nitrate. So the oxidation state of the metal, well, first we have to understand that because nitrate, NO3, is a -1 anion, that means the whole complex charge is +1. And so if the complex charge is +1, then we have to look at what the charges of these ligands are. Br is actually bromide, -1. Cn is cyanide, -1. So there's 2 of them, -2. Another 2 of them, -2, for a collection of -4. If the whole thing has to have a +1 charge, then the iridium has to be +5 overall, right? So +5, and then 2 of that positivity goes away with the bromide to take it down to +3, and then 2 more with the cyanide, so +5 is our answer. Coordination number is simply how many ligands are attached to it, 2 and 2, 4. There we go. Okay, circle any ligands of this list that can be chelating polydentate. And so now we need lone pairs, Lewis bases, that are separated by at least one or 2 atoms. And so sulfate, O, minus, again, because it is nonlinear and we have 4 atoms that can potentially surround it, that can be most likely a bidentate ligand, so that's 1. All right, H2S has 2 lone pairs, but it's on the same atom, which means it cannot be chelating or polydentate. Here we have, again, sulfurs are going to have lone pairs on them. They're bridged by 2 carbons, so that clearly works. And then thiocyanate, if you did the Lewis dot structure of that, carbon, double bond here, that's a double bond there, hard to see, and then there. And so because the Lewis dot structure with 4 bonds, 2 double bonds around that carbon, poorly drawn here, but atom, so that's linear, and because these are linear, that does not work. So that means that the only ones that could make more than 1 coordination bond are the sulfate and then this dithiol ethane. All right, would you expect the complex described above and a different complex with now 3 bromines and 3 waters to be the same color or different color? And so recall that these coordination complexes tend to be colored because of the energy gaps between the HOMOs and LUMOs as a result of d orbital splitting that these transition metals have when coordinated by these ligands. And so what affects the energies of these orbitals are obviously what the metal is, and then what is bound to it, how many of them are bound to it, and then the geometry of what's bound to it. And so because we have different ligands, different coordination numbers, and therefore different geometries, the energy between the HOMO and LUMO will be different. And again, we're not asking here whether it's greater or lower or whatever. You can take inorganic chemistry to figure that out. But we do know that there's enough different in here so that that will indeed be 2 different colors. And so I'm not going to write that out. Hopefully that's helpful.